Hey, we'll be doing the next part today, and I've called that sprints, right? Because we're really gonna be doing this in 30-minute sprints. Or at least, I mean, that's gonna happen quite often, I guess, because I'm gonna, it's just difficult to find that sort of like big groups of, big chunks of time in the day to deal with these topics. But let me open up the PDF and we'll get started where we left last time. Which was the 1.1. Yeah, exactly. And it was number 2. So I have initially particles in the state with this wave function and ensure the probability density is independent of time. Now the probability density wave function, right? This is another story. It's like if you want to try to understand where that comes from. No, not that, not unpassing. Damn it. Probability density wave function. So let's see whether we can pull up the dashboard in case there's anyone with questions. If not later, once this is uploaded. Because this really kind of comes back to the Born rule, right? And which is kind of a rabbit hole in and of itself, which I do want to go to, but it's not necessarily an easy thing to do within 30 minutes. It just isn't interpreted as the probability density, sort of the the squared norm of that, right? Give me a second. Just too many things open. So yeah, that's kind of like the squared norm of these, right? And so we assume this is what we have. This is the initial time, right? And then so the thing is, what I kind of say is like if psi of x. Oh god, give me a second. It's really laggy. If psi of xt, it's like it's this kind of thing where like I can't ever remember, right? So it's like this kind of like a coefficient times an initial condition, right? So that's how I'd start that part based on what I did in the first part. Like and knowing that a is this kind of like exponential with whatever like eigenvalue or whatever like not eigenvalue but like Hamiltonian. And then there's this kind of like I and h bar or something coming from the Schrödinger equation, and that's kind of like something that there's a t in it, which is just the only thing that it means is like that generic expression is that initial state with this operator applied to it, right? And this is a matrix, so exactly. And so now we're given this, and like I think I'm going to kind of ignore that for now. So I'm just going to focus on this part here, which is this what's saying 1 over the square root of 2, and then this is kind of like psi 1 plus psi 2, I think, right? I think that's the starting point. Yeah, which is basically means like it's a superposition of both, and we have to show that that the probability density is independent of time. And so now we have to calculate that, which, like, to be honest, I'm not entirely sure I know how to do, because these are wave functions, right? So you usually say like there's this kind of a plus b squared thing, right, where you have like that rule. Yeah, like that it's but that's just for rational numbers or whatever, just numbers, right? So you can have, yeah. Exactly. So a squared plus 2 times ab plus b squared. Like, I'm going to go ahead and assume that that applies here as well. That's as far as I can go so far. So I'd say, of course, I'm assuming that coefficient, that coefficient goes all over the place. So you kind of have like, so you have like, that square would be like 1/2 of like psi 1x plus 2 times you know, 2 times, I guess, 1/2 and 1/2, right? So it's like it's still a half, right? So whatever, times like psi1x and times psi2x, something like this, and then you've got like psi1x, right? Like the thing is, I don't like that is independent of time anyway. Like first, yes, it was yesterday, 2 days ago, I don't know, a couple days ago. I kind of like at a high level, I was reasoning like, okay, so it can be like the particle is you know, sometimes governed by this, sometimes governed by that, sometimes governed by that, which kind of like governed by I don't know if you could interpret that as being governed by both at the same time, so an overlap, right? Which you would kind of then think, maybe you'd think that that's something that you can just say, well, because we know that they are non-overlapping, then that term doesn't apply. Sorry, I don't know. The socials were a bit visible down there, but I'm not so sure. Like what I know, so what we can say is if the regions are overlapping, right, then the two wave functions like psi1 and psi2 don't overlap either. But like that's independent of time anyway, right? You know what I mean? It feels like it maybe it's the first problem in the set, and maybe I'm just overthinking it again. But I just say it's obvious just out of the fact that that's the initial state, and the initial state is not time dependent. So I even correct my own, you know, what I just said yesterday, that like that if there was an overlap, you'd get time dependency. But again, that's the point of, I think that's what we're trying to do and see. So I don't know, we'll see. To me, that is kind of in a way, it feels obvious. But then it's like C says, now assume that two regions overlap partially, and starting with the same like wave function as in case B, show now that the probability density is periodic. It's a periodic function of time. So actually, it depends on it. It's time dependent, which bothers me, unless there's something to do with the overlap of two wave functions, right? That is the thing. Or unless we say, yeah, wave function overlap. Maybe there's something there. So wave function overlaps are widely used in the field of non-adiabatic dynamics, where allow the evaluation of state-to-state transition probabilities without the need of computing. It seems to be a thing, right? Wave function overlap. Oh, God, I just hate that. Energy splitting. Okay, physics stack exchange. Let's go for that. High school are trying to understand what happens with two-wave functions overlap in account of two protons being accelerated towards each other and smashing them together. So a wave function is a mathematical model. It's a complex value function. To see what it describes, let's calculate the complex conjugate. Okay, so to see what it describes, one has to calculate the complex conjugate square of the function so as to get a real number function. The squared function gives the probability of finding the particles at x, y, z, t. Oh, so the complex conjugate square. So when there are more than one particle to describe a new calculation, yeah, but that's not what I mean. It's we're talking about a single particle here, and we're talking about the state of sort of being in a superposition of of states, right? That's what's okay. So is there a generic wave function representation, something that we can expand our psi1x into? Position space wave functions. Oh, look at these. Okay, that's okay. Now we're talking. So is here we actually I didn't know that. So it's actually okay. So you have to calculate the transpose. So you do that. It's like the transpose. You got to calculate the transpose of that. So that's definitely wrong. That's definitely wrong, right? So to do that, what I'd have to calculate first is the transpose of like the initial state anyway, right? Um, hmm. Yeah, but how do I calculate the transpose of that? Adjoint of a wave function? I keep getting lost with the namings of these. Come with a wave function. Ah, okay, so you have to. Why the complex conjugate though? Okay, so we actually have a. Okay, cool. So we actually have. Yeah, I mean, I could use that as in like I could assume that there is a time dependency in a way, right? Because I could assume that's a free particle, right? So then we kind of have this term that being sort of the generic. It's something that I could use to unpack these. Mm, Although it's like eigenfunctions psi x, right? So there's no time dependency in here, but like that just might be falling, because then here they assume time dependency, so they just say t equals 0. I'm not so sure the whole eigenfunction here thingy, but I'd say one could expand these to that, right? And then calculate the. So how exactly should I rationalize this and come up with a good generalized concept of what a given function? I know it's complex conjugate. At the same time, I think generic concrete examples will be found in my head. So for every x and t is a complex number. Is the conjugate of that number, no more, no less. The reason it seems like sometimes it's not the t part that gets conjugated is simply that often it is the only part of the wave function that is complex. Let's use your examples. We want to calculate psi star, complex conjugate. So, well, since the conjugate of the product of two numbers is the product of their conjugates. Okay, so let's do it step by step. Okay, so yeah, that's what I'm missing. So the conjugate of the sum. Okay, I think. Give me guys a second.